What does a mathematician interested in waves have on their toast? You guessed it, it's geometric spread. What's going on here is that we've got some source of a wave, and it's emanating outwards in a spherically symmetric manner. We ask what the intensity at some distance from the source is, right? We know a couple things about intensity. Namely, that the pressure perturbation squared divided by the divided by something to do with the impedance is the intensity, right? So all we got to remember out of this is this idea that the intensity is essentially the square of the pressure perturbation, right? And then we've got to remember that the perturbation is small on the background of on a background pressure, etc., etc., etc. Right? We know all of that. We're considering a spherically symmetric wave, and what we're going to do is we're going to write down the wave equation in spherical coordinates. So this is my pressure perturbation. I'll put the prime there once just to remind us that it is in fact perturbation. We've got some coordinates for angles. We've got some time. Right, and we've got the wave equation. We're going to just ditch these and remember that it is the perturbation pressure. We're just going to use P for my writing convenience. We're also going to assume spherical symmetry. That is, that the angle is unimportant. There's no change with respect to the angles themselves. The only dependence is with radius and time. So we're going to ditch this. We're going to rewrite the gradient in spherical polar coordinates. So it looks slightly different to our normal gradient, but we can look it up on Wikipedia. And for the radial component, we find right, you get this r dependence popping out, and you get this first derivative term as well. All right. So what we've reduced our problem to is understanding what pressure is out here, right? So we're being lazy. We're not looking at intensity anymore. We're looking at pressure as a function of radius. So we don't want to solve this with separation of variables. We could solve it, but we're lazy, and I'm pretty sure there's a better way. And the better way is to convert this into a standard wave equation, right? So the standard wave equation would look like that, right? So we've got to figure this out. Now, there are ways and means that you can do this in the forward direction, but since I know the transform, I'm going to spare you the pain of that. And just invite you to consider this variable here, r times p, so the radial coordinate times the pressure. So to find the first derivative of this, because we're aiming for the second derivative, right? So we want to find out what this term is and compare it to this entire equation up here. So in order to find the second derivative, I've got to find the first derivative first. So I now have to do this with the product rule because I've got this as a function of radius and time. R is just a function of radius. And that'll be important later. So we use the product rule, differentiate the first function, leave the second one alone. Then we differentiate the second function, leaving the first one alone. Now, because we want the second derivative of this, we've got to do it again. That one becomes easy. We've still got to use the product rule here. Right, dr is just 1, so we can get rid of that. Then we've got r d squared p dr squared. Okay, so we're actually quite close now to the form of our equation, except the r is in a different spot. Right, if I go and look up and compare, looking at this one here, and we're comparing it to this one here, right, we see that I've got this term, but my r isn't here. I've got the 2 there, but I don't have the r. I've got an r here, but I don't have, and I've got the second derivative. Sweet. Looks like this, if I just divide this by r, I get that left-hand side. But what happens over here is a bit sus, because I've got to divide both sides of my equation. However, if I note dq dt equals r dp dt, because q is just r times p, but r is a constant relative to this dt operator. So r is just a function of radius. It's not a function of time. So if I want to calculate the time derivative of q, I've just got r times the time derivative of p. So the second derivative of q with respect to time is then this. And I notice that I can indeed take this equation here, multiply by r, and then I've got an equation to do with q. This is then d squared q dr squared, and this is 1 on c squared dq dt. That's the standard wave equation. So I've reduced my not so nice spherical wave equation back to the normal wave equation. In one dimension, right? One spatial dimension. So let's go ahead and solve it. we know that it's going to be an amplitude times a complex exponential. Just like that. But we don't want this weird arse variable q, we want pressure. So we rewrite. And we find that our solutions look like this. Our pressure is some wave that decays with radius. Right, so this is for some fixed time. We've got the sinusoidal component, or the e to the whatever component. Then on top of that, we've got a e to the minus whatever. Oh, sorry, that's not an e to the minus whatever, that's a 1 on r dependence. So overall, our pressure looks like something like this. Right, a sinusoid with a 1 on r decay. Now this is pressure, this is not intensity, but we know the intensity is related by the square. So what we're going to have is intensity is proportional to the square of pressure. So that is I prop 2 a on r squared e to the something like so. We don't really care about this. This is just a wavy bit. What we care about is this. This is how the amplitude or the volume of the sound is decreasing. So it's decreasing like an inverse square law, right? And that's what we mean by geometric spread. As our waves spread apart, the intensity, just from the fact that it's following the spherical idea, our volume is dropping very rapidly.